welcome to lecture number 43, and as I told you in my last lecture that we are trying to solve network problems with the help of Laplace transform. That is another way, nice way and very popular way of solving network problems. We will see, because I have not yet started Laplace transform, but I told you about some standard functions for like that unit step function, which is like this. This is ut. Then I told you about unit impulse function. This is delta t. 2 delta t, if somebody wants to sketch 2 delta t, 2 into delta t, just this height of course towards infinity, but 2 times strength of the impulse is said to be 2. Similarly, 2 ut is the strength of the unit step is 2, you understand that. Now, and these axes are of course time axis. Then I told you that you can have a shifted version of unit step function. For example, this is a signal which is u t minus 2, where this is 2, this is time, shifted to the right, and this is the value of the function. Similarly, you can have a shifted delta function here at 2. This can be written as delta t minus 2. So, this is how these functions were developed, and properties of one of the properties, there are several interesting properties. If it is needed for some problems, I will further go into that, but one property I told you that if you multiply x t with delta t and integrate it from minus infinity to infinity, it is going to give you the value of x 0. That is, wherever this delta function is situated, delta is situated at t equal to 0. So, that value of time it will give for the value of x. Similarly, minus infinity to infinity, if you integrate x t into delta t minus 2, it will fish out the values of the function at t equal to 2, it will be x 2. So, you have to examine where this delta function is situated, and if it is multiplied with any other general function x t, the corresponding values of x can be found out. Another function just I will mention is called a ramp function. Ramp function. Unit ramp function. It is like this. With respect to time, the function will linearly go, and it is called r t. Slope is 45 degree, that is at 1 t equal to 1, this is also equal to r t is nothing but t for t greater than 0. So, it is a 45 degree line, and is equal to 0 for t less than 0, that is the value of the function is 0 for t less than 0, that blue colored, then it ramps up as time passes. So, this is so these two things combined is called a ramp function. So, all the functions we are considering is essentially a causal function, causal signal which exists for t greater than equal to 0. For t less than 0, the functional value is 0. Similarly, for any function which exists from t equal to 0, this is x t, this is a causal function. Okay? And the causal signals we can say also like this. For example, if I ask you to sketch sin omega t, if I simply ask you to sketch, you will sketch like this, is it? And sin omega t, this is 1, this is minus 1, it oscillates between minus and plus 1 with a regular frequency, angular frequency omega radian per second, that is fine, this is the time axis. Okay. But this is what I am telling is not causal, because here the function exists for all the time minus infinity to plus infinity. But suppose somebody asks you to sketch a signal sin omega t, same sin omega t into ut, then he is going to sketch like this. Sin omega t ut will be like this. And for t less than 0, this will be 0, simply because you are multiplying this function with a unit step function, is not the functions, this is 1. So, the functional value for t less than 0 is 0 here. So, 0 into anything you multiply gives rise to 0. However, for t greater than 0, you are multiplying sin omega t by 1. So, it will be sin omega. So, this is the function sin omega t u t. This type of signals will be mainly dealing with while solving circuit problems and try to use the Laplace transform. So, this x t is a general function, for example, that I have sketched sin omega t u t. Clear? See, you can play around with these functions. For example, a function like this, a pulse signal, rectangular pulse signal, this is my x t. If you say that, how can I express it? Suppose this is t equal to a, this is t equal to b, b is of course greater than a, as can be seen, this is this one. Now, this function x t can be shown to be, easily shown to be u t minus a, then minus u t minus b, because u t minus a is this signal. So, the value of the function for t less than a is 0 and u t minus b is this u t minus b, but negative of that will be this one. So, if you add these two, this will cancel out and give you this pulse. This is very easy exercise, you can easily see. So, many functions can be represented as a in terms of say unit step function or say ramp functions, things like that. For example, I will give you another interesting example. Suppose I say that a function is like this. a triangular pulse. Okay. This is time, this is your x t. So, this is suppose 0, this is suppose capital T. So, I can describe this function and let us put some number. Suppose this is 1 and the value of the function is also 1 here. How to represent this function in terms of either unit step or ramp functions like that. So, one thing is clear, this function looks like a, apparently it looks like a ramp function at t, okay, because at 1 this is 1, we have just indicated that. So, up to this point it is fine, ramp function, but after that the function drops down to 0 and maintains its 0 value for t greater than 1. For t less than 0, of course, the functional value is 0. Now, the question is, if you simply write x t is this one, that will be wrong, because x t is equal to r t if I write, that is not the case, because for t greater than 1 I have to make the value of the function 0. Now, how can I make this function 0? So, what you can do is this, at this point, that is t equal to 1, please follow me, you add another ramp here in the negative sense minus r, but it is a negative ramp no doubt, but shifted r t minus 1. Therefore, I will say x t is equal to r t minus r t minus 1. I can write it in this fashion. But if you add these two, this plus this, it will now give rise to this function. It went up to the value 1 at t equal to 1 no doubt, but after that this increment will be offset by this negative increment and it will remain flat. Got the point? So, x t is equal to r t minus r t minus 1 will be a function like this, which continues, but once again this is not this function, that is our original function I want to represent in terms of ramp, unit step function like that. So, that I have not yet achieved. What else I have to do? So, at t equal to 1 I have to add a, so that this portion vanish, I have to add a negative step, that is minus 1. So, this minus u t minus 1, this truly represents this pulse. Therefore, by visually looking at these curves, you can make it happen like that. Another alternative way of writing this, so ramp functions coupled with unit step function, you can manipulate them with your intuition and sketching the diagrams very quickly what it should be, how it can be represented in one line. In general, all these things means that you are trying to tell x t. In our older days, if I did not know the ramp function and unit step function, I would have described this function x t as x t equal to 0 for t less than 0, x t is equal to t for t greater than 0, less than 1, greater than equal to 0, less than 1, and it is equal to 0 for for t greater than 1. This is how this whole thing you are writing in 3 lines can be written in one stroke in this fashion. That is what I want to mean. Understood. Therefore, this is how one can write. Similarly, it is easy to see this R t. Another way of looking at it is this is the ramp function. It is certainly the ramp pulse 1. This is suppose 1. This is the original function. Same problem I am doing. This is 1. It is a ramp. You can tell that this is nothing but the multiplication of this. This is a ramp only R t, and multiply this function with this pulse, rectangular pulse. What is this rectangular pulse? This is 0, t equal to 0, this is 1. So, x t also could be written like this, R t into u t minus u t minus 1, because below this 0. So, it is giving this part during this portion, this unit step, this into 1, this into 1, it continues up to this. After that R t is present, no doubt, but you are multiplying with this function which is 0 here, u t minus 1. So, anyway, there are several nice ways of expressing functions in terms of some. These are called basic functions. You can represent some standard waveforms like square pulse, triangular pulse, trapezoidal pulse, and so on. So, we can do exercise on that. But anyway, now I will be telling you coming to the Laplace transform. Laplace transform. Now, Laplace transform is generally written. We will not go into deep detail. We will start with the formula of Laplace transform, because here only the solution of circuit we will be examining using Laplace transform. Now, how it is written as that, if you have a time varying function x t, the Laplace transform of x t is defined as minus infinity, this integral e to the power minus s t into x t into d t, that is all. And this is called double sided Laplace transform. Okay, in general, this is the definition of Laplace transform, and since if you carry out this integration with respect to time, right hand side you will be returned with a function which is function of s only. So, that is written as x s, that is the thing. Okay. But as I told you, if x t is equal to 0 for t less than 0 and is equal to x t, the function for t greater than equal to 0, then this integral Laplace transform, that is causal signal or causal signal, exists for t greater than equal to 0 and equal to 0 for t less than 0. If that be the case, then the integration This is the general definition of Laplace transform. Then this integral then can be written as 0 to infinity only e to the power minus st xt dt, and we call it xs. Okay. So, in circuit problem we will be doing like this. In other words, what I am telling is we are really finding out Laplace transform of x t into u t, because x t may be a general function for all time I can compute the value of x t, but make it a causal function. How can you make it a causal function? Multiply x t with u t, then only the value of this whole function x t into u t will become equal to 0 for t less than 0, and it will be equal to x t for t greater than 0, because u t being 1, and this is written as then 0 to infinity e to the power minus s t x t into u t dt. But this u t now no point in writing, because I am only considering the value of the function for t greater than 0. So, this is as good as 0 to infinity e to the power minus s t into x t dt, because u t is always equal to 1 for t between t equal to 0 to infinity. It is one and the same thing. So, this is how Laplace transform is defined. I am not talking about any circuit now, I am just telling, okay, given a function you can find out its Laplace transform. Similarly, if the Laplace transform, which will be function of s only, you can find out its inverse and come back to time domain. Now, the question is, what is this s? This s is called a complex frequency, s plus sigma plus j omega. Mind you, e to the power, you write e to the power anything. What is the dimension of this a? Dimension of a is 1 by second, is not 1 by second, sort of frequency. 1 by second is frequency. So, this s is called a complex frequency. And it is a complex number. So, s can be represented in the complex plane. This is the real axis and this is the imaginary axis. Some complex frequency plane, okay. And we can then find out Laplace transform of some useful functions and make a table of them, so that whenever I wish I will find out its Laplace transform, and we will see later how it simplifies the solution of differential equation problem. Now, now let us take a simple example. Suppose, and we will come back to this sigma plus j omega business once again here. Suppose I ask you that find out Laplace transform of unit step function. How much it will be? That is what I have been asked to find out. Then I will say Laplace transform of unit step function is equal to this integral 0 to infinity e to the power minus st into ut into dt. Anyway, ut is a causal function that we have seen. For t greater than 0 it exists. So, it is like this. Now, this integral, if you look at it carefully, it then can be written as 0 to infinity e to the power minus s t into dt, because u t is equal to 1. Acha, now this integration can be carried out e to the power minus s t and divided by minus s. This will be the integration, and then I have to carry out these values at t equal to 0 and infinity and take the difference. Now, that means I have to find out the value of e to the power minus s t by minus s at t equal to infinity minus e to the power minus s t by minus s at t equal to 0. This is what I have to do it. Is not. So, I have to find out these values. Now look at this first term e to the power minus s t. What does it do? What is it as t tends to positive infinity? That is what we have been asked to calculate. As I told you, e to the power minus s t will be minus sigma plus j omega into t, is not, that is what I told. Yes, I have to evaluate the value of this at as t tends to infinity. Now, this can be written as e to the power minus sigma t into e to the power of minus j omega t. Clear? Now, this quantity as t tends to infinity, I am sure about one thing. What is that? This quantity is some cosine omega t minus j sin omega t. Therefore, whatever will be its value will be like sin omega, cosine omega has got finite peak values, between that two only it oscillates. Is not, this will be finite values no matter what is the value of t, because see e to the power j omega t. What is the magnitude of this function? Magnitude of this is equal to always 1. Therefore, no matter what is the value of time, the magnitude of this portion is 1. Sigma is a real number, and if sigma is positive, then e to the power minus sigma t will tend to 0 as t tends to plus infinity if sigma is greater than 0. Is not, that is what it means. Got the point. So, this is the thing. At t equal to 0, of course, the second term is very simple. T equal to 0, put t equal to 0, e to the power 0, that will become 1. So, it looks like it will be equal to 0, the first term, and minus it will be equal to minus s, that is equal to 1 over s. So, we say Laplace transform of u t, as expected it will be only function of s, is 1 by s. That is what the final result is. Now, only one point I will tell you. In this derivations, when I talked about this, I saw that this integral will become this 1 by s provided sigma is greater than 0. Any value of sigma will do, 5, but it must be greater than 0, 2, 9, whatever it is. We will see in the analysis, if you want to apply Laplace transform, this sigma thing will be in the background, you need not worry about that, and that is called the region of convergence. ROC, region of conversion. So, for unit step function, for Laplace transform, that is, this integral will converge to 1 by s if the real part of this complex frequency is greater than 1, and in the complex plane we say that this is your real axis, this is your imaginary axis, and I will say the Laplace transform exists for sigma greater than 0, mind you, sigma greater than 0, not sigma equal to 0, just excluding the imaginary axis, any value of sigma will do. So, we will always presume that whoever is taking Laplace transform, he has in his mind that this condition is satisfied. Fortunately, it will be always in the background. You need not worry, you need not find out, you have to specify the sigma values specifically to find out the Laplace transform of a given function. No matter what is the sigma value which is greater than 0, this result will be unique. That is what I want to tell. Got the point. Therefore, this is the Laplace transform of unit step function. Similarly, let us take another Laplace transform of, say, Laplace transform of a shifted function, if you have understood me correctly. Suppose I say I want to take Laplace transform of u t minus a. This time this will be equal to, as we know, this integral is 0 to infinity, and suppose a is greater than 0. So, e to the power minus s t into u, that the value of the function u t minus t a into d t. This is what I have to do, is not? So, this will be this thing. Now, obviously, this integration, you have shifted the function to u t minus a, which means into u x t minus a, whatever it is like this. So, this function u t minus a, as we know, is equal to 1 for t greater than a and is equal to 0 for t less than 0, t less than a, I am sorry. This is known. So, this integration can be replaced by a to infinity e to the power minus s t into d t. This will be the integration, because u t minus a is 0 for t less than a. So, 0 to a, nothing will be there, this function into 0. So, this will be equal to then e to the power minus s t divided by minus s integration, and limit is a to infinity, like this. So, this will be once again equal to e to the power minus s t by minus s evaluated at t equal to infinity minus e to the power, same function, minus s t divided by minus s evaluated at t equal to a. Once again, the first integral, this one at t is equal to infinity, this will tend to 0, because s is sigma plus j omega. So, it will tend to 0. So, this will be 0 and this will become plus of Here it is simple, e to the power minus a s by s. So, Laplace transform of u t minus a is equal to, you can see it is e to the power minus a s by s. So, and above this, and we have seen that Laplace transform of u t is equal to 1 over s. So, this integral I have to only calculate to find out the Laplace transform of a given function. So, in general, now next thing what I will do is this, suppose Laplace transform of a given function x t, it will be some function of s. So, I write it as x s. Okay. Then Laplace transform of the shifted function is how much? Suppose I want to find out. So, I will do it like this. So, this is known, suppose this is equal to known, then what will be the Laplace transform of this function? I want to find out. Then how can I find it out? So, I will say Laplace transform of x t minus a, by definition it is like this, single sided Laplace transform x, please forgive me, x t into u t, Laplace transform of x t into u t is this one. I want to find out the Laplace transform of this function. X t is a function like this, suppose. Where will be x t minus a? Suppose this is a. The same function, its form will remain same like this, but it starts from here. So, this is x t into u t, that is what it is, and this is x t into u t x t minus a into u t minus a. Got the point? Same function, I am sorry, here it is slightly looks like different. You have understood the point. So, it shifted to right. So, how it can shift to right? So, shift x t minus a, if the car bodily shifts to right by an amount a in time domain, and then you multiply it with u t minus a, so that this part vanishes, causal signal. So, this is Laplace transform of this into u t minus a, I mean that. So, what does this mean? It means that e to the power minus s t into x t minus a into u t minus a dt. This integral I have to calculate. Obviously, u t minus a for t less than a is 0, is not? This is u t minus a. So, for t less than a, this is 0. For t greater than a, only this will become 1. So, that this integration then will be a to infinity e to the power minus s t into x t minus a into dt. This will be the thing. Clear? Now, to evaluate this integral, put t minus a some variable, say z, so that dt will become dz and t is equal to z plus a. So, put it here. So, this equation will then become equal to e to the power minus s, and for t you write a plus z into x t minus a. So, x z t minus a z, and this is t z. And what will be the limit? When t equal to a, z is equal to 0, and when t equal to infinity, z is equal to infinity. This will be the thing. So, you can write this integral as z equal to 0 to infinity e to the power minus s z into x z into d z. And this e to the power minus a, since I am integrating with respect to z, that can be taken outside this integral, is it? Now, this one is e to the power minus s. This is z is a dummy variable here, it can be changed to once again to t. How does it matter? Integration value will not change, x t dt, is not? Got the point. So, this is equal to e to the power minus s into x s. Therefore, in general, if Laplace transform of x t is equal to x s, Laplace transform of the shifted function, I mean x t into u t, I should not forget that to write, and shifted version of it will have same x s, but multiplied by e to the power minus a s. If a is a positive number, it will be positive number, and so on. Got the point. We will continue with this, and this is just we have verified earlier, Laplace transform of unit step. I found out it to be is equal to 1 over s. Then what I am telling, Laplace transform of u t minus a will be how much? E to the power minus a s by s. That is exactly we found out earlier. Anyway, we will continue with this, and this is very interesting. If you know these rules, you will be able to gain much more in solving network analysis. In some later lectures, we will come to that. Thank you.